Hey, it's my pleasure to introduce Evgeni. Today will be the speaker. He's talking about line ensemble in car space geometric last passage percolation.
Okay, thank you very much for the introduction and for the invitation. It's a great pleasure to be here. So today I will discuss some recent joint work with Zhongru Yang, who's a PhD student at Columbia, and my postdoc, Zhengye Zhao, who's not in the room, but we'll repeat what she did as well in the talk. What we investigated is a certain kind of class of problems that arises in what's called symmetrized or half-space geometric last passage percolation. So I'll start by kind of defining for you the vanilla model, which is the unsymmetrized version. And then I'll move on to the symmetrized or half-space analog of last passage percolation. I'll tell you what we can prove about it. And then in the end, if there's time, I'll tell you some of the ideas behind the proof. So first of all, last passage percolation is a model that depends on some background noise. In this case, it's given by an array of IID geometric random variables. These are the Wij's, and you should kind of visualize them as being arranged in the first quadrant of the integer lattice. So for each side ij, you have some Wij's, and these are independent geometric. I'll put them to be geometric with parameter q squared rather than q, where q is a fixed number between 0 and 1. And this is only because later in the talk, I want to show you some formulas, and I don't want to have too many square roots floating around, so I'll just square things to begin with here. Maybe one small point is that our geometric variables are allowed to take the value 0. So this is the probability mass function. Usually, geometric variables start from 1, but these ones will start from 0. Of course, you can always just subtract 1 from the usual one and then recover these. So starting from these vertex weights, we're going to build path weights. So first of all, what is a path? So it's just this finite sequence of vertices, V1 up to Vr, where basically when you go from Vi to Vi plus 1, you always move 1 unit up or 1 unit to the right. So these are directed paths. So this is the picture of a directed path in this model. And then the path weight, which is this W of pi, is just the sum of the vertex weights. So this path will cross some of the vertices, and you just add up all the vertex weights that you pass through along the path. And this is going to be the weight of pi. And from these path weights, we'll build what are called last passage times. So these are certain random functions, Gmn. So they depend on two arguments, little m and n, that are natural numbers. So for each m and n, you're going to look at the n by n rectangle that contains some of the weights w. And then you'll just look at all possible upright paths that you can draw in this rectangle, because the rectangle is finite, the number of paths is finite. In each such path, we'll have a weight, and you're just going to define Gmn to be the maximum such weight. Okay, so in this picture, I just kind of computed a few of the last passage times. You can kind of check by hand that the gray path here is an optimizer. It achieves the highest possible weight. Now, maximizers here are not necessarily unique. So for example, in this path, I could have gone, rather than go up by 1 and then to the right by 1, I could have gone down here to the right by 1 and then up by 1. And this will give me another path that has the same weight. So go ahead.
What are the inputs in the boxes? Are those?
So these are IID geometrics. Okay. That's the background noise, and that drives everything. And then from these, you build the path weights, and then you define this random function, Gmn, that is just the maximizing weight of the path that you keep using.
So later you add the expectation somewhere. Yes.
So later on, well, we're going to be interested in the asymptotic behavior of these random functions. That's basically what we're interested in, is what does this function G look like for large values of m and n? Okay, that's the essential question that we're going to be interested in. So before we kind of go to probability, let me mention that maybe you have seen this model if you have
we
some.
try to remove so.
Let me see. It is distracting, I imagine. So let me see if I can.
Press OK. Yes.
I can press OK. Okay. Thank you, Greta. So what I wanted to mention is that you may have seen this if you have some computer science background. So computing these last passage time is one of the first examples that students see when they're introduced to dynamic programming. So there is a very simple recurrence formula that relates the last passage time at mn in terms of last passage times at smaller values. Basically, what you do at each site. So let's just look at a simple example. So you start by initializing the boundary conditions of all g's are 0 outside of the table. Let's say you build these black values inside, and you want to compute the red values. So what do? You look at the cell that is immediately to the left or below. You take the max, so that's this max function here. So the max of 4 and 6 is 6. And then you add to that the corresponding W weight here. So this is the array of W's, you're building the array of G's from it. So the max of 4 and 6 is 6 plus 2, that's an 8. And the maximum of 6 and 4 is 6 plus this 0 gives you this 6. And the maximum of 4 and 0 gives you 4 plus 1, that's 5. So it's very easy to compute these values, and you can run a kind of polynomial runtime algorithm to generate these G's, and you can study asymptotics even numerically. Now, however, we are probabilists, so let's see what people have done with this model in the past. So one of the earliest models, not the earliest, but one of the earliest is due to Kurt Johansson. So what Kurt did is he kind of looked at what's happening to this function near a microscopic point n. So he kind of thought about this, he looked at the line that passed with the slope -1 through this point. So there's going to be certain lattice points that fall onto this line. And for each of these points, you can compute this G function. Okay, so now you have some sort of a collection of G's that you can map somehow on the integer lattice. You have some values of G's. And then you want to think about this as a process. So what do? You just linearly interpolate these points. So this is what he looked at. So now you have some sort of sequence of polygonal paths, piecewise linear paths. And what he was able to show is that if you take this sequence of paths, and you kind of horizontally scale them by n to the 2/3. So you take this picture and you kind of scale it this way by n to the 2/3 and vertically by n to the 1/3. Then this will have a functional limit. Now, this limit here is this capital A. It's called the Airy process. So the limit is not Brownian motion, it's something else. I'm not going to define it for you, but the Airy process is a certain continuous stationary process. Its path regularity is the same as that of Brownian motion, but it is stationary. It doesn't have a growing variance over time. And it's not important here what the constants f, q, and sigma q. These are just some simple algebraic expressions involving q. I'll show you some of these later in the talk. And these are model specific. The key takeaway points here are these scalings that you need to perform in order to get the non-trivial limit. So these 2/3 transversal and 1/3 fluctuation exponents are indicative that this model belongs to the KPZ universality class. And this is a vast class of models. It includes random matrix models, it includes interacting particle systems, directed polymer, random permutations, and so on. So I'm not going to talk about any of these here. Today we'll talk about just last passage percolation. Now, I do mention, sorry, was there a question? So I will mention that maybe the 1-point marginals of the Airy process is something people have seen. These are given by the Tracy-Whittam GUE distribution. So this is some sort of a stationary process. It has Brownian paths, but if you fix any time t, and you kind of look at what's the distribution of the value of this curve at time t, it's given by the Tracy-Whittam distribution. Okay, so this is what happens for full space LPP. Now it's worth mentioning that this Airy process, this will be related to my title, which is line ensembles, that this Airy process kind of actually naturally embeds into a sequence of many processes. You kind of construct in a natural way, that I'll try to explain on the next slide, some sequence of other processes for which this thing is the lowest index curve, which is kind of highest. And any sequence of random continuous processes is what we call a line ensemble. And this thing is what's called Airy line ensemble. So I'm not going to formally define this object for you, but let me tell you where it comes from. One way that you can obtain it. So here is a picture of what's called the Brownian watermelon. So you start with capital N Brownian bridges. They start and end at the same location, let's say 0 times minus n and n. And they are independent, but they have been conditioned to avoid each other in this interval minus n and n. Now, this is an event of measure 0. One needs to make an appropriate sense of this object, but you can. An alternative way to think about it is you can just run Brownian motion on the space of Hermitian matrices. And then if you look at the induced process on the spectrum, that's going to give you this watermelon. So if you run Brownian motion on matrices, you get what's called Dyson Brownian motion. You can have a bridge version of this that gives rise to this picture. And what Corwin and Hammond did about 10 years ago is that they kind of looked at this model and they looked at the edge scaling of it. So if you kind of again move to the edge of this picture, you scale horizontally by n to the 2/3 and vertically by n to the 1/3, you see that the top curve of this ensemble will converge to the Airy process, maybe minus a parabola. Maybe if you kind of look at this picture, you see that there is some curvature going on here that you need to kind of correct for. But also the second curve will converge to something, and the third curve will converge. And all of them jointly will converge to this object, to this Airy line ensemble. And this Airy line ensemble, it has a close neighbor, which is given by the parabolic Airy line ensemble, which is just you take the Airy line ensemble and subtract the parabola. So you should think about that the Airy line ensemble is globally flat. It's a stationary process. And if you subtract the parabola, it looks like an inverted parabola. So the parabolic one looks like a parabola. The one without parabolic is just globally flat. So this, as I said, I'm not going to define formally this thing, but this is one way to define it. It's the weak limit of these curves. But I do want to discuss one important property that this ensemble possesses, which is a certain invariance, resampling invariance. So what's the story here? So you fix 2 times little a and b, and you fix an index k. So let's say in this example, k is equal to 5. So I'm going to freeze the kth curve, and I'm going to erase the top k minus 1 curves between times a and b. So I obtain a picture that looks like this. And now what I'm going to do is I'm going to sample independent Brownian bridges that connect the red dots. So these are the B1 sub to B4, and they're independent except that they have been conditioned to avoid each other and also avoid the kth curve here, okay? So in this way, you obtain a new ensemble, and the essence of the Brownian-Gibbs property is that the law of this new ensemble is the same as the old one. So you have a local description of the Airy line ensemble in terms of avoiding Brownian bridges. Now this property might seem very simple and just an exotic property of this ensemble, but it's essentially a defining. And this is a kind of an important breakthrough work by Amol Agarwal and Jae-Young Hwang from last year. I mean, the paper appeared on the arXiv in 23, but basically what they showed is that this parabolic Airy line ensemble is up to an independent affine shift, the unique line ensemble that is globally parabolic and satisfies this resampling property. So you should think about this. This is a classification result in the same spirit that Brownian motion is the unique process that is continuous and has stationary and independent increments. So it's kind of a qualitative description of this ensemble without formulas. Okay, so this is kind of the picture in the continuum. But we had this LPP model. So we know that the top curve appears, at least from the work of Johansson in LPP. What about the other curves? Where do they come from? How do we see them in the LPP model? And in order to do this, it's a complicated story to motivate why what I'm going to tell you here is the right thing to do. So, in order to fully appreciate why this is the correct object, one needs to understand what's the RSK correspondence in Green's theorem. But what I'll do is I'll just tell you where these things come from, and I'll kind of force you to trust me that this is the correct object to look at. Okay. So what you do is you introduce higher rank last passage times. How to think about these things? So your rectangle is like a room. You have tiles in the room, and you put geometric number of cookies at each tile. You put the child in the corner of the room, and you tell them you can only move up and right, collect as many cookies as you can. That's your first last passage time. Now, if you want to build higher ranked last passage times, instead of one child, you put k children. You still play the same game. You tell them you can only move to the right and up, but you cannot hit each other, right? So the paths that you follow need to be disjoint, and you collect all together as many cookies as you can. And that's going to be your kth order last passage time. In formal language, this is just the maximum over k vertex disjoint paths that are all contained in this rectangle. Okay? And now you might object and say, well, what if my number of children is too big? What if they don't fit in the room? Well, then you just declare the last passage time to be the sum of all the weights. So for the moment, the number of children is equal to the side length of the room. So in this picture, for example, the smallest side length of the room is 3. You can always collect all the cookies with 3 children. And you can build 3 paths that cover everything. And so if you have more children, there's nothing to be gained. You just declare the last passage time to be the same. Now, these GKs are not going to be what converges to the Airy line ensemble. Instead, you need to look at their successive differences. So you define lambda 1 to be G1, and all additional lambdas are going to be the differences of 2 consecutive Gs. So this is how many additional cookies can I collect if I had 1 extra child kind of going from k minus 1 to k children. And the statement is, and this is a theorem due to Delvernik and Farag, that if you look at these lambdas, then under KPZ scaling, they converge to this area line of sum. Okay, so this kind of explains, maybe at least after the fact, why this is the correct object to look at in this model. Now I should mention that this is, again, not just some inconsequential statement. This type of convergence on the level of line ensembles is an important ingredient. There's a hierarchy of distributions or kind of objects that you can look at. So at the bottom, you see something like Tracy-Whittam. Then you see the Airy process, which is the top curve. Then you see the Airy line ensemble above it. But then you can go higher. You can go to something called the Airy sheet, the directed landscape. So there's a whole ensemble of kind of higher and higher notions of universality and convergence that you can put here. And this one is kind of an important stepping stone. In fact, kind of in this hierarchy of things, the bottleneck is almost always the line ensemble. They have some black box theorem that allows you, once you know convergence of ensembles, you can kind of lift it all the way to something called the directed landscape that I'm not going to talk about. But okay, so this talk is not about, however, LPP, it's about symmetrized LPP. So how do you define that? So I'm going to change the story in two ways. So the first thing that I'm going to do is I'm going to introduce a second parameter C that is just going to be between 0 and 1 over Q. And my W's are still going to be independent geometrics away from the main diagonal. On the main diagonal, so this W1, 1, W2, 2, 3, 3, 4, 4, and 5, 5, and so on, these are going to be now geometric with parameter C times Q. So I have an extra parameter to play with. So this is kind of a benign thing to do. Now, a serious thing that we're going to force in this picture is the symmetry condition, which is I'm going to insist that my W's form a symmetric matrix. Okay? And so what's going to change in this story? So a lot of the things, of course, I changed the background noise. The behavior will change. But the functions that I'm going to look at are exactly the same. So I can still play the same game as before. I can define my path weights the same as before. I can define my last passage times the same as before. And I can build my sequence of lambdas the same way as before. But one kind of crucial thing that happens here is that because the W matrix is symmetric, that actually forces the G matrix to become symmetric. So if you look at these last passage times along these red squares, kind of going into the right, they're going to be equal to those going up. And this is not equality in distribution. This is almost sure equality. It's a deterministic statement. And that just kind of comes out from the way that things are defined and the fact that W is a symmetric matrix. And similarly, if you look at the green cells going down, they'll have the same last passage times as the green cells going to the left. So what this means is that if you want to understand the model in the quadrant, you can forget half of it because it's symmetric anyway. So you might as well just focus your attention on the octant. And this is why this is sometimes called half space LPP, because you're starting from the quadrant and you're removing half of the space and you're focusing on the octant instead. Now, one thing that also happens when you kind of think about the model this way is that on the octant, the main diagonal plays the role of a boundary, right? And so this parameter C that affects how large are the weights on the main diagonal is going to produce a boundary effect that will affect the asymptotic behavior of the G's. So something will change depending on whether you have big weights on the diagonal or small weights. And there's going to be a phase transition, basically when C is...
How the C is defined?
How the C is just a fixed number. It's between 0 and 1 over Q. And the only reason I'm insisting it's less than 1 over Q is so that this parameter in this geometric is less than 1. So I can kind of make sense of it. So it's just an additional parameter you put in the model.
Is it completely obvious that the G is symmetric? Because the initial is not symmetric when you play. Yes.
Let me think how obvious it is. I would say pretty, because you can, if you look at any path that, is an optimizing path like this, you can kind of reflect it with respect to the main diagonal. I am horrible at drawing, so my apologies. I don't know how to draw symmetric things at all. Let me try to do it. And then the weights that you collect are the same because the weights are symmetric. So any path here can be, that is contained in the n by n. So this one is kind of contained in m by n. This one is going to be contained in n by m.
Because I'm thinking like when m less than n less than m, because so initial is like this, yes.
Yes.
So when n is smaller, it's quite straightforward. Everybody just move to the right.
Yeah,
Yes.
but you can move up, right? So you can do this or you can do that. So if you have a point, let's say M1, you have a single path, it's going straight to the right. But if I have the point 1n, I will have a single path going straight up. And then the weights of those two paths are the same because the W's are the same. So the W's that I collect here are just omega y is equal to the W's that I collect here. So
I know, I'm thinking that when n less than m, because the initial is just, it's 4 here, so that everyone move to the right. But when you flip it, your initial should still be here, yes, but it's not a 4, so then you need to design the path. Do you see my point?
So I don't know what the initial is.
So it's a,
I think
The box.
sorry,
I think Gentle means you start with a rectangular box.
right?
If it's a square box, you have the symmetry.
right.
No, but so you can have two rectangles that look like this, right?
Right.
So GMN. So this is my point. MN is looking at paths that are contained in this rectangle. And then I have GNM that is built using weights from this rectangle. But this
Okay.
rectangle and this one have
K
this.
equal to 1, I completely agree. It's obvious. So for general K.
I mean, again.
So I guess the question is, are you starting from the vertical?
Yes, that's not obvious.
Yeah.
That's not obvious. That you need to, yeah, okay, so now I understood. There is a preferred direction the way that I explained. So I wanted to give you a simple story with children collecting cookies, but then I need to specify a choice. So one can show that the starting points don't matter. So you can start these paths anywhere inside. Now for concreteness, it turns out that you can always obtain a maximizer by arranging them in this way, but you don't have to insist on this. Now that's not an obvious thing to do. We spent 4 pages proving it at some point. When I was first learning about the LPP and RSK. But yeah, that's a good question. Sorry for not understanding the question for as long as I did. Okay, so what I was kind of basically saying is that you'll get different regimes depending on what the value of the boundary parameter is. If the boundary parameter is small, you have a subcritical regime with one kind of limit. If it's bigger than 1, you get a different limit. And if it's critically scaled, you get a third limit. So we were not the first ones to kind of think about this problem. There are some earlier works. They go back to the early 2000s. There's 3 papers by Bike and Rains. The first 2 focused on random involutions. So these are permutations that are equal to their inverses. And they were interested in longest increasing sequence for these things. But in the third paper, they did investigate this geometric symmetrized LPP model. And they were focusing on, and maybe I should explain what they were doing. So they focused on what's happening exactly at this point on the main data. And what they saw is that when C is equal to 1, they get one limit, which is still kind of related to random matrices. It comes from the edge asymptotics of the Gaussian orthogonal ensemble. And when C is between 0 and 1, they get the asymptotics of the Gaussian symplectic ensemble. So this indicates that there is a transition, that when you go from C is less than 1 to C is equal to 1. And they also kind of investigated what is the nature of this transition by kind of blowing up what's happening at around 1. And they obtained one family of distributions called crossover distributions. Now they chose, not they, but later on people chose the parameter var pi. Do not ask me why they chose this parameter, but this is, we're stuck with it now because it's tradition. But you get the one parameter family indexed by this parameter var pi that interpolates between the GOE, GSE, and also the normal distribution when it goes to infinity. Now later on, Imamura and Sasamoto, they looked at this model, but only for the value C is 0 or 1, right? So they didn't kind of cover the full interval. They only focused on 2 values. So what they were interested in is, okay, Bike and Rain studied the 1-point asymptotics. And they asked, well, what can we say about multiple point asymptotics? So kind of you look at this process and you look at several times, can we prove a joint convergence? And they looked at kind of 2 regimes. One is when you pick a point of the form kappa n, comma n, So this is some macroscopically separated point. So here kappa is going to be something between 0 and 1. And what they saw is that you in fact, under KPC scaling, converge to the same Airy process as before. And the intuition is actually quite clear. If I'm macroscopically away from the main diagonal, right, so I have this main diagonal here, then basically I don't feel its effect. So I behave as if I don't have a boundary. I behave like a full space model, so I converge to the full space limit, which is this Airy line ensemble. Now they also focused on what's happening near this diagonal point, and they kind of obtained some multi-point expressions for the joint CDFs that are given expressible in terms of what are called Fredholm-Pfaffians, which is some summation identities that they were able to obtain for the two values of C is equal to 0 and 1. And later on, Betea, Boutier, Nejad, and Vuletic kind of investigated the critical scaling near this point N, and obtained kind of a one-parameter family of joint CDFs that kind of generalized these crossover distributions from a single point to many points. So they had some formulas that you can use to recover Imamura and Sasamoto's result for special values of R pi, or kind of limit of R pi. So when kind of me and Zhenge kind of looked at this, we thought, okay, well, there's some interesting phase transition going on. But all the results so far only investigate what's happening for the top curve. But we know we can build these ensembles, right? So we can do RSK and build these higher rank last passage times. What do the other ensembles do in this phase transition? So that's the question that we wanted to understand. And as I said, you can actually simulate this. So we can run this on a computer, and this is what we got. So the left picture here basically depicts these ensembles in the subcritical regime, when C is less than 1. And what you see is that they kind of stay together and everybody's happy. And when C is bigger than 1, so this is the right side of this figure, then what happens is that the top curve kind of separates from everybody else and does its own thing, and everybody else stays the same. Now the intuition here again is somehow maybe a little bit less clear, but still somewhat clear. Because if you have one child, and if you have a diagonal that has a lot of cookies on it, that child is going to go and collect all of those cookies. And then when you insert a second child into the system, they cannot take advantage of what the first one did, right? So that fat diagonal with many cookies will already be eaten, so they cannot collect as many. So basically, they behave as if they're in the subcritical regime. And of course, rigorously proving this is somewhat challenging, but we did manage to kind of basically completely understand this picture. Now, I should say that there is one important thing we don't know how to do. So we can understand the left side of this picture, which is between 0 and n, and we can understand the right side of this picture, which is from n to infinity. And this kind of corresponds to whether I'm looking at the red.
That was with, my glasses aren't here. That was with, which doctor? Remind me.
Maybe I can mute them.
Yeah, yes, and I think.
I don't think I have authority to do that. Do you have authority?
I did.
Okay, thank you. No, they forgot to turn off the sound. It's obvious. So anyways, what I was saying is that this corresponds to whether you're looking at red paths or green ones. So we can kind of analyze the green part and the red part separately, but they should be correlated, and we have no idea how they're correlated with each other. Okay, so that's a caveat in terms of what I said, that we can basically understand this picture. Now, what are the kind of main results that we can show? So this is the result by Zhenge. So what Zhenge did is she investigated first the subcritical regime, kind of looking at this situation where you're looking at the macroscopic point away from the main diagonal. Don't read the formulas, look at the picture. And what she was able to show is that all the curves converge to the area line ensemble under KPC scaling. So this kind of generalizes the result by Imamura and Sasamoto. So they kind of only looked at finite dimensional convergence of the top curve. She looked at all the curves, not just finite dimensional sense, but kind of in a functional limit sense, in the appropriate space of continuous functions. And also, they kind of only focused on C as 0 or 1, and she could kind of cover the full interval. And as I said, here are some examples of what these constants that I was hiding before look like, right? So they depend on kind of Q and kappa in a very simple way. Right? If I told you what is Q and kappa, you can just by hand compute all of these things and you can tell me what they are. They're not really important. Now, okay, so what about the supercritical regime? So if C is bigger than 1, what's going to happen is that you'll actually develop two regions. One is between 0 and kappa naught, and the other one is between kappa naught and 1. So kind of if you're very close to the 0, so that means you're far away from the diagonal, so you don't feel it, and then the curves do stay together and converge to the area line ensemble. So this also was shown by Zheng He. And then in our joint work, we kind of investigated what's happening on this interval when I'm close enough to the diagonal to actually be affected by it. And what we were able to prove is a curve separation phenomenon. We rigorously established that the top curve kind of goes off to infinity, and then the second one becomes the new first. The third one becomes the new second. And basically these ensembles again converge to the area line ensembles, but you have to shift the index by 1 because the first one just flew off to infinity, you lost track of it. Now we can compute everything here. Here's a formula for kappa naught. Again, it's not particularly illuminating what it is, but it's a simple formula in terms of C and Q that you can get.
What's lambda I?
Sorry?
Again? What's lambda I again?
Lambda I.
Yeah.
So these were how many additional cookies per child do you get? So if I insert an ith child, the additional number of cookies that I get is lambda I. Okay, so that's our discrete ensemble. And then you can ask, well, what about the top curve? What is it doing? Well, this guy is actually converging just to a Brownian motion with drift. So if you kind of subtract a linear term, so to remove the drift, then you kind of scale horizontally by n and vertically by square root of n, you'll converge to just a standard Brownian motion. Okay, so that's kind of what's happening away from the diagonal. And then at the diagonal, me and the Zombru investigated kind of the asymptotics of these ensembles at criticality. So kind of what's happening around 1. And kind of what we obtained is that, if you perform horizontal scaling, you should imagine that your ensembles, they start from the diagonal and they move to the right. So they're kind of defined on the interval from 0 to infinity. Okay. So they're defined on R plus, and we obtained kind of a brand new object that should be like a half space analog of the area line ensemble. We call it the critical half space area line ensemble. Again, it's a complicated thing to describe, but it's some sequence of random continuous functions, except that they're not defined on the whole real line, but only on R plus. Now, I do want to mention some of the properties that they have. We can describe them quite well, although not maybe as well as the area. So one thing is that we have access to finite dimensional distributions, but one needs to kind of express them the right way. And the kind of a correct structure to look here is viewing the ensemble as what's called a Pfaffian point process. So let me tell you how that story goes. So this is a picture of your ensemble. It's just a sequence of random continuous functions on R plus. What you do is you fix finitely many times, little s1, s2, s3, and so on. And you draw vertical lines through these times. And they're going to intersect your ensemble with some random points. These are the orange dots that you see in the picture. And in this way, because the ensemble is random, those dots are going to be at random locations. And this is what we call a point configuration, random point configuration. And one way to think about it is you can just put a unit mass at each of these red dots and think of this as a random measure on R2. And how does this work? Basically, if you give me any Borel set on R2, I'm going to draw it, and then I'm going to count how many of these red dots happen to land inside of it. So this is exactly this formula here. You have a sum over the intersection points that contribute 1 every time that point lands inside of your target set B. And in formal language, what we can show is that this random measure has the structure of a Pfaffian point process with reference measure that's given by the counting measure on the S's times the Lebesgue measure. So each of these vertical lines carries a copy of the Lebesgue measure on it. And then we have a formula for its correlation kernel that I'm not going to even try to write down. It's given by some, big contour integrals that are not too bad, but, do take a lot of time to get used to. Now, I'm not going to pretend that anybody here knows what's a Pfaffian point process, but let me tell you what kind of information do you get by knowing that something is one. Basically, you can look at R pairwise disjoint Borel sets and just compute the measure of each one. So this is just counting how many orange dots land in each one. And you can express the joint moment of these variables, right? So these are now integer valued random variables because they're just counting the number of red dots. And you can express them as an R-fold integral of a Pfaffian. If you don't know what a Pfaffian is, I can show you at the end of the talk, but it's just some generalization of the notion of a determinant of this kernel. So if you know the kernel and you know how to compute Pfaffians, in principle, you can compute these moments, and one can prove that these moments uniquely characterize the finite dimensional distributions. Okay, so we have one description of this thing. This model also has a kind of interesting Gibbs property of its own. So kind of the boundary creates a different type of resampling that this model enjoys. So let me try to describe that. So as before, I'm going to fix a time t that is positive, and I'm going to freeze all the curves of index, let's say here 4 and higher, and the value of the top 3 curves at time t. And then I'm going to ask these 3 curves between 0 and t, what is their conditional distribution given everything else? And the answer is that it's going to be given by 3 independent reverse Brownian motions with alternating drifts. So what's happening here? So here basically your Brownian motions are reversed because you're going from time t back to 0. So you're just kind of reversing time in Brownian motion. And then the drift of the first one is going to be equal up to some constant minus var pi. So I guess formally it's minus square root of var pi. The second one has a drift of plus square root of 2 var pi. The third one minus, the fourth one plus. So they alternate. So kind of what this, one way to physically think about this is that if var pi is positive, then the first 2 curves, the first one has a negative drift and the second one has a positive drift. So they tend to attract at the origin. If r pi is negative, then the first one has a positive drift and this one has a negative one, so they tend to repel at the origin. So there's basically the reverse Brownian motions, except that they have some sort of an attractive or repulsive interaction at the origin. If r pi is 0, they're just vanilla Brownian motions without any drifts. Now, of course, they have been conditioned to not intersect each other. This is always the case in this business. But we have this kind of local description or analog for the Gibbs property in the half space setting. So let me pause here, see if there's any questions. This is kind of the end of the main result, all the results parts of question. Not all of them are main, but. Yes.
Just to clarify, you say you condition on all long curves or just?
So you condition on the first 3 curves to the right of t and all the curves on all of r plus. So you kind of look at this box, the index set corresponding to this box is 1, 2, 3 for the first 3 curves in the interval 0, t. So for all Lij with ij outside of this box, you condition on that.
I'm just curious if that's the same as what you wrote when you condition on the n+1 curve, on just the n+1 curve.
You can show that they're the same. So the kind of conditional on the kth curve, the stuff above it and under it are actually independent. I don't think that anybody actually wrote this down, but it's true. And one can easily show it for discrete models, and then by continuity, it will extend to continuous ones. Okay, so in the last 10 minutes or so, let me tell you something about the proof. Okay? So at the high level, what we're doing is we have these lambdas, right? These are our random discrete ensembles, these random piecewise polygonal paths that look like this. And I'm just going to shift them around and scale them. So these are how I form these LIs. This is just kind of performing this horizontal, n to the 2/3 and vertical n to the 1/3 scaling. So these are now random piecewise linear kind of polygonal paths. And we want to show that they have a functional limit. And there's not really a lot you can do here. Basically, you have to play the same game that you play in Donsker's theory. If you want to show that which is the statement that random walk trajectories converge to Brownian motion. And the way that proof goes is you show finite dimensional convergence, and you prove that your sequence is tight in the appropriate space of continuous functions. This is, by the way, how these paths look like. They're not that bad. Better drawings than whatever I can achieve on the board. Now, the main kind of, and this is a very loaded slide, hopefully I can at least get through this one, is the main input that allows you to do anything in this model is a connection between geometric last passage percolation and Schur processes. And this is kind of an old idea that has been kind of rediscovered over and over again. I'm not going to explain precisely how this where it comes from, but it originates from the RSK correspondence, which is some bijection between integer matrices and sequences in Young diagrams or sequences of interlacing partitions. But let me at least tell you what is the consequence of this. So now this is a crash course on Schur processes, so we're going to need some definitions. So a partition is just a decreasing sequence of integers that is eventually zero. We say that two partitions lambda and mu interlace if lambda 1 is bigger than or equal to mu 1 is bigger than lambda 2 is bigger than mu 2. So there's exactly one mu between two consecutive lambdas and vice versa. A Schur polynomial, I'm only going to define it for a single variable, x. It takes as input two diagrams, lambda and mu, and it's going to be zero unless they interlace. And if they interlace, it's just x to the power of the weight of lambda minus the weight of mu, the weight being the sum of all of these lambdas. So it's just a monomial up to an indicator. And the last thing that I need is a boundary monomial that is again just a c to some power that you build from the sequence of lambdas. And what is kind of the magical formula that makes anything work here is that if you draw a downright path, so these are the vertices of a downright path in this picture. So for each of these vertices, you have a random collection of lambdas. So you have a sequence of partitions that is indexed by the vertices of this path. And you can ask, what's the joint distribution of all of these lambdas? So that's the probability that you see here. And the answer is that this is expressible as a product of this boundary monomial times the product of q, where each of the q's is just a skew-Schur polynomial in one variable, where basically if your path goes to the right, your lambdas need to increase, and if the path goes down, they need to decrease. So basically the difference between these two terms is whether lambda I is bigger or smaller than lambda I minus 1. So this might look like a just useless identity. How do you even begin to use this at all? But these distributions of this form have been studied extensively. So they fall into the framework of what are called Pfaffian-Schur processes that were introduced by Borden and Reins as Pfaffian analogs of the determinantal point processes introduced by Okunkov and Reshetikhin a few years before that. And basically, what one can the immediate advantage that you have from looking at these processes is that they are known to have a Pfaffian point process structure. So you have access to formulas that you can use to compute things. Now, as I mentioned before, the formulas that you have do look like this. They look like, the expectation of some joint moment is expressible in terms of some Pfaffians. So this is still not obvious. How do you extract finite dimensional convergence from such a formula? And that requires some massaging. But kind of a couple of years ago, I was able to develop some sort of a black box framework that allows you to study, extract finite dimensional convergence from kernel asymptotics. And the sort of strategy goes through kind of completing three types of steps. The first one is showing that the measures converge in the vague topology, whatever that means. And then you want to show that your particle locations are tight. So that's kind of the second and third point, establish that the locations of these particles are tight. And if you have these two ingredients, then basically you can prove finite dimensional convergence. Now, let me first say that in order to establish the first point, you can just analyze the kernel. You have contour integral formulas. You can use method of steepest descent. This is kind of standard at this point. And kind of if you know that these kernels converge sufficiently fast, you can conclude vague convergence for point 1a. Now you can ask, why do you separate tightness from above and below? And the reason is that even though we have formulas, they're not useful for doing everything that you want. So maybe just to give kind of an example, this is a toy example. So if you look at the function, kind of the formula for e to the t. So this formula is very good for proving that e to the t converges to infinity as t tends to infinity. Right? Because most of these terms will blow up, all of them come with the same sign, so of course this is going to blow up. But it's very bad for showing that e to the t goes to 0 as t tends to minus infinity. Right? Because these terms, they're going to blow up in absolute value, but they'll come with opposite signs. There will be a lot of cancellation, so it's very hard to use this formula to prove this statement. Right? And so something similar happens to us. So our formulas are very good for probing upper tail distributions. And just by kind of using the kernel, we can prove something like 0.1b. But for proving tightness from below, which is requiring that we investigate the lower tails, we need to do something else. And there's kind of a slick idea that, no, I shouldn't really say it's slick because I came up with it, but working idea that if you know that your limiting point process has infinitely many atoms, then you can conclude tightness from below. So as I say here, for the upper tail distributions, you just need to understand the kernel asymptotics, the upper tails of the kernel, and you can win. For the showing that the limiting process has infinitely many atoms, in the papers with Zhengye, that came for free because the limiting process is, this area, the slice of the area line ensemble, which is the area point process. People know that it has infinitely many atoms, so that's just 30-year-old result due to Tracy and Whittam. But in the paper with Zongru, we didn't know this because we were building this new ensemble as we were running the argument, we were creating the limit itself. So we didn't know any properties that it has. And then we kind of had to argue, why does this thing have to have infinitely many atoms? I don't know how much I can explain this idea, but kind of the strategy there was to show that if you look at these ensembles, so you kind of pass through some subsequential limits, and you look at an increasing sequence of times. And what we were able to show is that as you increase the times kind of along subsequential limits, the number of surviving particles needs to go down. And just stochastically needs to go down along subsequences. So as I move away from the boundary, the number of surviving particles decreases. But what happens as we move away from the boundary? So as I move away from the boundary, I stop looking like a half-space model. I start looking like a full-space model again. And one can show that these things have to converge to the Airy process, which has infinitely many particles. So you have a stochastically decreasing sequence of number of particles that decreases to infinity. The only way that that's possible is that it was always infinity to begin with. You cannot decrease to infinity to be finite at any intermediate point. So this is at a high level what we did. So this kind of takes care of the finite dimensional distribution in the convergence of the argument, kind of in the framework that we had before. We had this, where do I have it? Yeah, in this general strategy, this takes care of point 1. And then for point 2, which is tightness, again, actually, the proof of tightness comes out of the Schur formula in some different way. And kind of if you spend 5 minutes looking at this formula for skew-Schur polynomials, maybe even less if you're more familiar, and you think about, well, what's the conditional distribution of the lambdas on, in a string of lambdas given the starting one and the ending one? And because of this expression here, you'll see that you're going to get some telescoping of the terms. So only the first one and the last one will survive. And because you're conditioning on this, they will get absorbed into some normalization constant, and you get that the conditional distribution of the lambdas on any interval, given what's at the beginning and at the end, is just uniform subject to interlace. And then if you spend another 5 minutes thinking about, well, what does that mean? You realize that what this is basically telling you is that the local distribution of the lambdas is given by interlacing geometric random walk bridges. Okay? And this is what we call the interlacing geometric Gibbs property, which is like a discrete analog of the Brownian Gibbs property. You replace Brownian motions with geometric random walks, you replace avoidance with interlacing. And then once you realize this, you can play games, because in the business of Gibbsian line ensembles, we know how to analyze such systems. And again, kind of maybe a couple of years ago, I developed some sort of a black box theory that says that anything that satisfies this discrete Gibbs property, this geometric Gibbs property, and has kind of one-point tight marginals, which we know how to do from the finite dimensional convergence, is necessarily tight in the space of continuous functions. Now, this argument relies on some sort of a strong KMT type coupling between random walk bridges and Brownian bridges. So the vanilla KMT coupling comes from coupling random walk trajectories with Brownian motion. You have a similar type of result for bridges. That's due to, again, myself and Xuan Wu from 5 years ago. And basically, you can apply this framework directly to study LPP. That's kind of why it was built, so that you can study different types of Schur processes in different settings. Because we consider one type of boundary condition, one can consider periodic boundary conditions. So we have a kind of a black box theory that should work for pretty much all types of boundary conditions. Now, one thing maybe I should mention in the context of the paper with Zhongrui, the story was even simpler. So somehow we had a different way to think about the ensemble, where we could view that as reverse geometric random walkers rather than random walker bridges. So we didn't even need some sort of bridge theory to complete the story. We can just use vanilla KMT, the usual KMT. The particular result we used is due to Shao. And so that's how you get tightness. Now, let me summarize. And what I try to explain to you is, at the high level, what is symmetrized LPP? It's a model that depends on two parameters, Q and C. That's a boundary parameter. From this, we build some sort of complicated collection of random lambdas that were our discrete ensembles. And these lambdas behave differently depending on whether C is smaller than 1 or bigger than 1. If it's smaller than 1, they kind of stay together. And you have vanilla type of area line ensemble limit. And when C is bigger than 1, one of them separates. There's a curve separation. It kind of goes on a tangent and does its own thing, goes to Brownian motion. And then at criticality, near the diagonal, we obtain kind of a brand new object, this half-space area line ensemble. The main inputs are RSK and Green's theorem, kind of mapping the problem from LPP to Schur processes is